4 institutes that we have, and where your teachers have their home place, their research home place. My name is Jürgen Müller from the Institute of Geodesy. In German it's Erdmessung, and we use the abbreviation IFE. I'm the director of this institute, and I will give you a flavor on our research topics. If you have questions, you can interrupt me. Please ask me at any time. Okay, our institute is placed in the neighboring building. This a little bit bigger one on the right-hand side. We are sitting here, and you look out of the window to this building 3109, and here in the 4th floor we have our offices. We also have one of our seminar rooms, right, the most upper level. Okay, so someone, maybe you will also have a tour to the various buildings, and then you will also visit our building. Okay, our main topic is that we are interested to survey the Earth's surface as a globe, and then the question is, how do we look at the Earth as do we take a geometrical perspective, or do we take a gravimetric perspective? So that means, do we look at it as we see it, and then is it a sphere or anything different? But we are mainly interested to also observe the gravity field of the Earth and include some gravity field quantities in our surveying techniques. So we want to determine the Earth's gravity field, and we want to use it. So one of our tasks is to work with this shape of the Earth. It's called GuG. I will explain it later in a little bit more detail. But we are also interested in the motion of the Earth. That means the Earth's rotation, for example, the variations of Earth's rotation. So normal people mainly do not know that the Earth does not rotate homogeneously, but indeed we have variations, changes, which have an impact on our daily life, also for navigation purposes. So we have to know the gravity field. Also, this is not known to everybody, that the gravity field is not the same, but I will try to explain it in a little bit more detail. Okay, so what are our observing methods? We want to determine the size, the motions, deformation of the Earth. We want to determine its mass distribution inside the Earth, on the Earth, and which methods do we use? Normally we are using satellites, and what you may know is GPS satellites, so that we use, as you do it in your mobile phone, we do our positioning, our navigation, if you look at maps, using the GPS system. And we do the same, but on a more scientific level. And similar, for weighing the Earth, for determining the gravity field variations, we also use dedicated satellite missions. And this is just one example. So this is our methods, and we have also different methods on the Earth surface. And what is also very much relevant is that we need a certain class of reference systems or coordinates to do all our calculations, to determine point values on the Earth's surface, to model the Earth's gravity field. But you may know that we also need to use a certain kind of coordinates to do some mapping of the real world into some maps. But this will be covered, this special task, by a different institute. We are more interested in G and measuring the gravity field. And what you see here on the left-hand side is first that what the deviation, it's shown here, what the deviation of the Earth's global shape is from a sphere. So we have some flattening of about 20 kilometers on the north and south pole. This is approximated by a body which is called ellipsoid, rotating ellipse. And what we now need is even the gravity field related quantities. That means a deviation of the ellipsoid and what is called geoid. And the geoid is the ocean surface, so the ocean in rest continued beneath sea continents. So that's like a lake which starts at sea level and goes through the Earth. And this is our height reference surface. And on the right-hand side, you see this surface, the differences of this surface related to the ellipsoid. And it is here for Germany, difference between 30 and 50 meters roughly. So we are in Germany above this dark black ellipsoid by about 50 meters. In other cases, we are below this surface, 100 meters below or 100 meters above, and so we are interested also to determine this special surface. But and why is it relevant? And maybe you can look at this example. It shows you two surface points which you can observe using GPS. And you see, they may have little h1 and 2 is the same height. But does it really tell you if there's some water flow from one to the other or no water flow? It doesn't tell you this, because for a physical height reference, you need a relation to the ocean surface. And here is, and this ocean surface, which reflects some equipotential surface, some static reference. If you continue it through into the continents, then it is heavily affected by the mass anomalies. So this reference surface for the heights is affected by the mass distribution. And if you then, and in reality, we take our heights from this surface. And we see capital H1 and 2 are different. This means now, indeed, you have water flow from H1 to H2. But if you only use your mobile phones, your geodetic quantities, your geographic quantities, then you could not decide on this. So you have to learn how to determine those reference surfaces and how to determine these height values in reality. And the basic principles normally are already presented in our bachelor courses. Okay, at our institute we have 3 professors. We cover these various fields which I briefly introduced. Physical geodesy as my topic, and space geotechnics, for example. We also analyze data where we drag from Earth to the moon. So we carry out distance measurements, not we, colleagues, to the moon, and we analyze it. This is one of the research topics of Mr. Singh sitting here. And then we also study space geotechnics, the space sensors, the gravity field, as I mentioned already, but also positioning navigation plays a major role. So this is our team. You see, we have 3 professors, the upper line, and me, I'm in the middle. And we have a huge team, and Mr. Singh, for example, is here. It's an alphabetic order. Okay, a big team to do all these tasks. And now I give you just 1 or 2 examples more for each of the fields of the professors. And as I told you, we are very much interested in this reference height surface, this geoid value, and we use terrestrial measurements. These are those devices with which we can obtain gravity values on ground, and we use satellite observations, because also satellites react on the mass distribution on the Earth. So they are faster or slower. And then if you do all the data, we can compute these reference surfaces, which we need for our heights, which we can also need for other things. And the other things, so are illustrated here, because the gravity field is not a constant. We have mass variations. That means also the attraction of the mass changes. And one example is, for example, that you have some mass changes due to precipitation in the seasons, for example, in Amazon, but more prominent might be the ice mass loss in Greenland and the related sea level rise. And all of this is related to mass changes. So we are also interested in techniques to observe these mass changes on a global scale, but with some regional effect. And on the right-hand side, our height systems are illustrated. So worldwide, we have many, many different height systems, and we have to combine it, or we have to relate them to each other. And all these topics, in our case, are also, all these tasks are not only fulfilled by us alone, but also in combination with, for example, physicists. So we have big research programs like this TerraQ program, where we study new techniques to observe the gravity field from space, or new kind of gravimeters to observe gravity field on ground. And then a very special technique is that we also can use clocks, so ticking rate of clocks, to observe this gravity field. Because Einstein told us that our clocks are depending on the distance to the Mars, and if I go closer to the Mars, then the ticking rate of my clock is changing. Not this one, also this one, but it's not accurate enough, but others. And so this is a completely new technique in geodesy that we may apply in future. This is an example from my colleague, Professor Fleury. Says starting, for example, sensors in such a gravity field satellite mission. One of them is called GRACE Follow-On, and you see there's a lot of technique inside the satellite. For example, there's an accelerometer device which measures accelerations, and they study that the raw acceleration that's shown here shows some perturbation and have to be corrected, or the perturbation have to be understood and then corrected. And if you can do it, then you have this nice behavior, which shows a kind of acceleration of the satellite. This is just one example of their activities. Another example from my colleague Professor Schön, who is working with GPS and GNS systems. They do positioning for any kind of vehicles, for satellites, for ships, for planes, but also on ground. They also analyze these GPS signals to understand better the troposphere, the signal path, the propagation, and then we can also use those signals to learn more on the atmospheric behavior. And we also have a system to calibrate those antennas, GPS antennas. Also some calibration for scientific use, but also maybe GPS antennas that you may have in your mobile phones. So you can check it there. And what we also do is we have a close collaboration between these various institutes, and one joint project is called IC Sense, where many measurement techniques, laser tracker, laser scanner, on which you learn more in the following presentations, is combined, where many observations are combined and analyzed to do some certain survey in the streets, to see also variations and support navigation and all those things. Okay, I already mentioned that many of the tasks are so huge that we really have many research bundles. So big projects, Excellence Cluster, or this IC Sense or SFB, because we need the collaboration with other teams, with other groups from physics, from geoscience, with other geodesists to get our work done. And the colors on the right hand side also show some funding from the German Space Agency, from the European Space Agency. So we have many third-party funding to do this research. You might more be interested in teaching. So we cover many of these topics also in our courses, so that you really learn how it works. So each time we include new research findings in our courses, and for this is Bachelor and Master, as you can find on the web pages. And if you zoom in, you can see our courses. Some of them are only in German, but most of them are also in English. So you can follow them as you like. But maybe this topic will be addressed by anybody else. So let me summarize. I just wanted to show you, give you an idea of what we are doing at our institutes, IFE, in a nutshell. So you see the figures of what we are doing, what we plan. And if you really want to understand it, then you can visit our webpage and you can ask questions to me. When I now have finished this part on the Institute of Geodesy, I should also mention I'm the chair of the exams board. So I'm responsible if you run your exams, if not everything works properly, or if you have some proposals to make changes in certain courses, if you want to collect certain courses, if you're not happy with your grade, or whatever, then my board, I'm the chair of this exams board, we are responsible for this. But you can contact us, and also me, not only as professor of geodesy and Erdmessung, but also in this context. So you're welcome at any time. So I would like to stop now. Thank you very much, and maybe you have questions now, or from abroad.
There's no question in the chat right now.
No. So for you, it might be rather new, everything. And I know that especially our institute is far away from some classical survey, because we address some, let's say, some funny topics with this gravity field variation. We also are collaborating with the physicists to even elaborate even more funny measurements techniques, like using clocks for some geodetic survey, or using some kind of quantum gravimeters. So we let atoms fall to observe the Earth's gravity field. So many of those funny things. But somehow it might become relevant for you, and maybe you're already now interested, and then you can visit some of our courses. And some of our courses are mandatory anyway. Okay? If you have no questions, for you it's interesting to start your study. So welcome again, and then I hand over. You want to start now already?
I think we started at 11:30, so I have to wait for Mr. Voss to.
Mr. Voss will join.
He will share, or
Okay.
he will join me.
Okay.
But I need some time to prepare my notebook.
Okay.
Yeah, hello. Also from our side, as Professor Müller today mentioned the global part of the geodesy, we're now gonna land on the Earth, and we're gonna take more terrestrial measurements like laser scanning, for example, and tachymetry, leveling, what we have here. But we have also one part, I hope one colleague is coming and join me. This is it's Professor Voss from the real estate, from the land part, and he may explain you about also these parts. We at the Geodetic Institute are in the engineering geodesy part, in the statistic part, and also in this real estate and land part. There's Mr. Voss coming. Hello, Herr Voss. Hello. I just started with the first slide, explained who we are. We are from the Geodetic Institute. And yeah, I will start with the first part, and then Mr. Voss will take over. Okay, what we are doing is in geodesy and geoinformatics, we are in the field of mathematics and physical orientated, what also Mr. Müller explained. In the engineering, we can tell, or we can say we are engineers, and we are geoscientists too. And we have strong parts, and we link to computer science, of course, to legal and environmental and social scientists. That's what Mr. Voss also will give you more in detail. Yeah, just it's not the best view, but just to give you a small overview what we have. We are here as the whole Leibniz University. And we have faculties, and this is our faculty, the Faculty of Civil Engineering and Geoscience. And the civil engineers have 14 institutes. We also cooperate with them in some project and some scientific stuff. But we look at the geodesy, and this is divided into 4 institutes. One was still presented. It was the Institute of Geodesy Mr. Müller talked about. We are the Geodetic Institute, and you have 2 institutes more coming here and explain you the photogrammetry and geoinformation, and the Institute of Cartography and Geoinformatics. This is our staff, our colleagues. I'm here. I forgot to introduce me. My name is Jens Hartmann. I'm represent Mr. Neumann, who is one of our professors, who is the head of the engineering geodesy and the Auswertemethoden, which is the more the statistical part in our institute. Oh, sorry. And then we have Winrich Voss sitting here, who will give you later the instructions about the real estate and land side. Okay. Yeah, here we have also Mr. Neumann in as a picture. And yeah, this is the engineering geodesy and the geodetic data analysis. And I want to show you some real small examples or tell you something. Geodesy always, what we teach here is a statistical assessment and the optimal combination of this. And also of the evaluation of these measurements. At one side you have measurements. These are one part, but then you step into the data analysis process and you're going to calculate. Mostly we do it with least square method. This is based on Carl Friedrich Gauss, and yeah, you see the old German currency, it's 10 marks. I have it here in real. So geodesy was honored with the old 10 German marks, and this is Mr. Gauss on it, the very famous mathematician, and he was also his work was also dedicated to the geodesy, and you see also a trigonometric network here on the no, es ist nicht scharf, okay. And the old sextant. And yeah, it is real. We are here for a couple of 100 years and making good things for the world. Yeah, and just to give you a small example, what we do is a 2D coordinate transformation. I explained the least square adjustment. At the end, you want to have this result. We start here with two different coordinate systems, and we will transform it into, or let's say the orange system into the blue or black system. And we need these parts. We need to translate it to shift this origin to the second or to the coordinate system we want to end. We have these two translation parameters in 2D case. You can also have it in 3D. Then it's a little bit more, but this is just a simple example. And then afterwards, we need also a rotation, what you see here. And yeah, you see it is nearly perfect. We have it transferred to transformed to another or to the final coordinate system, but we need some scaling, and after some scaling, which is the fourth unknown parameter, and afterwards we have this result. We have a good transformation. We want to have it optimal, so we're gonna minimize it. And as observations, for example, I forgot to say these are maybe the observations are the coordinates of the house. And then we need a minimum 4 equations, but mostly we have more equations, and then we have this minimization and estimation of the parameters. This is one small, very simple example. Yeah, I mentioned two parts, the engineering geodesy part and the data analysis. Here for the engineering geodesy, we have, or what we do is measuring with some instruments. What we have, you know, may terrestrial laser scanners, and you may know tachymeters and leveling instruments. That's what we have also. But we only we're not keeping only our interested onto instruments. We also or you also learn the methodology based on that instruments, the measuring methods, and also you can see it as a process chain, the tools and the data analysis of this. Yeah, and engineering geodesy can be from the start, from planning to the construction, and also we have monitoring phases afterwards. The building is still there, but you may want to know how much deformation you have, for example, a dam or whatever. I will show it on the next slide. And to summarize it, you can say it's a life cycle, for example, of skyscrapers, tunnels, and bridges. Yeah, and that's what we see here. We see a sluice here, a dam or a gate. It's more a gate. and you see the deformations when the water is in. Then the gate is deformation, or there's a deformation. You can see it here in this plot. It's going to be it's in the range of some of meter. It goes in the direction. Yeah, this is 1 meter deformation, and it's a lot. And you also have it on bridges. This is a bridge which can be lifted up, and you may want to know the deformation to these parts when it is down in the, let's say, 0 phase, and then you lift it up and you want to know how much deformation is going to these pillars here. And this was also one nice project here, an old train bridge. We worked together with the civil engineers, not only from our university. It was a very big project with some other universities from Darmstadt and Berlin. This was pulled down by some hydraulic infrastructure, and we measured the deformations of this old bridge, which was an a stone arc construction, and we compared these measurement results with the results of the civil engineers, which have different ways to monitor the deformations, and just to validate geodetic measurements. Measuring results with civil engineers was part of this nice project. A lot of papers was published by this one, so it was very successful. Yeah, to give you more examples, we have this dam, for example, I mentioned here. You have different water levels, and then the dam is deformation, or there's deformation, of course it is, and you may wanted to know how much deformation, and just to make sure that the dam is still there after a high level of water. Also the wind wheels we have here, you may know it, but I can tell you it's definitely there are deformations for these wind wheels, and you also have to keep in mind that the materials, you don't want any damage, so you must from time to time to map the deformation. Deformation modeling is one part, and you have also the building documentation to measure old churches, for example. Here you have a nice 3D 3D object model. This is also one part what we have also for the industry. For example, ships and planes are mapped and checked for the quality, for example. And to give you, I mentioned the sensor by themselves, which is laser scanner. It goes more in the direction of multi-sensor systems. What we have here, laser tracker and laser scanner together for mobile mapping. Also the UAV-based multi-sensor systems, which are equipped with cameras, laser scanner, and then the data afterwards were fused or will be fused. And also for a crane path here, this wagon is gonna map the crane path here, and to also map the damages, or may do some repairing of the crane path, because it's very heavy ones, and there are definitely damages, and you wanted to know it by time to make some repairing. And we have this quad here, which is a very efficient way to measure 3D bigger, larger object, and then afterwards fuse the data. These are the sensor systems. What we have just to give you a small rough introduction, what we have of models, lecture models. Introduction into geodetic data analysis is the first one, the smallest one, but then we have the kinematic measurement process in engineering geodesy. There are also, this is also what I showed you with the multi-sensor system. We have a project seminar, which is more done by student groups. And we have these lectures here in the data analysis, recursive state estimation for dynamic systems, analysis of deformation measurements. I explained these deformation measurements in detail with a couple of examples here. And we have selected topics of geodetic data analysis and engineering geodesy. Currently it is in German, but I may join if you know, or if we want to learn German. Industrial surveying is in English. It's very interesting, very nice part of geodesy and calibration of these multi-sensor systems. When you have two sensors, you need definitely a calibration between these sensors. Yeah, that was my part. And now Mr. Voss with the land real estate management will step in. Okay, Sie müssen hier quasi nur stehen. Ich weiß nicht, Sie sind ein bisschen größer als ich. Sie sehen sich da selber noch im
Ja, that's okay. Passt, ne? Okay. Hello, ladies and gentlemen here in the room, and maybe at the screen also, ladies and gentlemen. My name is Winrich Voss. I'm the professor here for land management, as we call it in short terms. And I want to explain a little bit on that topic to you. You can say our topic, you can have a title over it. It's all about land is a topic we can put over it. And when we talk about land, you know that land is subdivided into plots. And the plots are normally in individual ownership. There are plots which are in public ownership for roads, for example, or train lines. But there are also a lot of plots which are in private ownership, especially where the people are living and working. We want to talk, or we have to deal for a sustainable development. That's what we all want to have. How could we implement a sustainable development? It's a topic in the Sustainable Development Goals in the world, and good living, and all these things are depending from land and from the availability of land, from the price of land, which is and how it is available. And all these are the topics of the land management courses. And we also have very many international views to this topic, because the problems are different. In Germany, what is the main topic in Germany when we talk about land management? It is the high prices on the property market in the big cities in the moment, very hot topic, discussed very much. Or after the floods in this year, we also talk about protection of properties against flood risks and things like this. On the other hand, in the rural areas, in many countries, not only in Europe, but especially in East Europe, we have problems with the migration. The people are leaving the rural areas, and how could we have good living conditions also in rural areas? So these are also questions. We are looking at the towns and the urban areas, but also at the rural areas. And if we have an international view, there are a lot of problems with securing land rights, for example, with things like informal settlements or land grabbing, and all these topics we will talk about in a seminar course where we are working with contributions from the students, and this as a base to discuss all these topics and to find solutions how to improve it. The German, the knowledge of the German system is of course good. Is it good to have it? But it is not necessary in detail. But of course, we could find, we could look at good solutions, and some of them are also in Germany. Okay, so this was a general explanation of the land management, and you also see that the real estate management, the property market, is a very central part of it, because the property market and the possibilities to earn money on the property market is a very strong incentive for many owners, and if this is not in line with your general situation, then you will not reach your sustainable development goals. Okay, so in our part we looking very much at legal situations, legal frameworks, and also at environmental situations, because sustainable development means also to have an ecological, correct and future possibilities, and the social science are also part of it, because we have to work with the people. The people are determining in the end, the owners, especially the landowners, what is possible and what is not possible. So the property rights, the people and institutions, and this is, you already know this, the 17 goals of the Sustainable Development Goals, especially number 11 is very interesting for us, or number 15, for example. And the aim of all these studies of you is that you should become an expert for land, for property, and for development, so that you are able to work together with architects, with urban planners in future, and with investors to organize new urban and rural development. In principle, we differentiate in land management, which is more or less a view to a bigger amount of plots and a new urban or rural situation, a village, for example, or a new neighborhood. And in the real estate management, we are looking more or less to one plot or to single plots and single ownerships, how they influence the whole process. The basis for all is the geoinformation about land, about property, and about real estate. So this means the cadastre and the land registration system, but also the valuation. How could we determine the value of a property when we change planning, for example, and there is much more stories are possible on a plot and things like this. This is how in the subdivision of plots is done. This we use when we want to organize things like this. We have a new plan. This should be a new neighborhood we want to implement. And this is the existing property structure, property right structure and plot structure. And we have to change it into something like this, where the roads are in a public ownership, although this area has not been in public ownership before. And this is not only a topic of expropriation. Expropriation is not the first tool we want to use. We have other tools to work on that. This is what you should get to know. And we need a balance between the private rights and the private belongings and the public belongings of the society, of the civil society. That's what these are, different procedures we get to know, although for urban areas, but also for in rural agricultural situations. Okay. Of course, you also need a lot of land for infrastructure, for public infrastructure. Here is the extension of the Frankfurt airport with this new place for landing, which needs 300 hectares of forest in this case. And how to implement things like large projects, this is also our topic. Or very important, do we have enough locations for windmills to reach the aims for the energy turn which we strive for? So this is very concrete and very important aspects of organizing a process, also with science, science-based process, how we start from planning to implementing and to using a plot in a sustainable way. The nature aspects are very important, of course, and each nature conservation needs land, land which is normally not in the interest of a public stakeholder to keep it in his ownership. So we also have to look at things like this. And I already mentioned in the beginning the problems on the housing market in many countries in the world, especially in the big towns. On the other side, we have the rural areas with less demand and too much supply and shrinking prices, which is also not in the interest of a sustainable development. So we will talk about the housing market in some of our courses too. These are a short overview over the program in the master courses. We have an obligatory part which is in the second, in the summer semester, depending from your beginning. So, and this is the land management and real estate economics, which is a course where we talk about development of new areas in the cooperation between public side and private side, different models we are talking about. Especially the international view is implemented in the land tenure and land policy topic. I already talked about that. We have a wide range of international topics there, and also in the rural and village development. The program in German, if you are able to talk German, then we can talk about this topic here, and the project seminar was already mentioned. In the moment we have a topic on wind energy projects and how to implement them with civil society. Okay, I hope you have an impression of the whole area, which is wide, and you may choose between different topics when you have your own contributions in that, and the general framework is done especially in this course. And for the students which have no pre-knowledge on these things, we talk about some literature for you to come into the topics so that you can follow the stuff, the materials. Yeah, so this was the introduction of the Geodetic Institute in Hanover with 3 main parts. 2 has been introduced by Jens Hartmann, and the land management part I tried to introduce to you. And so here in the room, questions are possible. From outside, I think questions are not possible, isn't it?
Questions are possible. I asked the chat if there are any, but so far there are none.
Okay, then I would like to finish this presentation. Thank you very much.
Okay. So, hello guys. Hello guys online. Yeah, let me start by introducing myself. My name is Dennis Wittig. I'm working as a scientific employee and researcher for the Institute of Photogrammetry and Geoinformation, short IPI. You may be wondering about the second I that comes from earlier days when the institute actually had a different name. Ingenieursvermessung was the second word, and then the name got changed and we used the I in the geoinformation to make the abbreviation still correct. Yeah, it's my honor to welcome you, not only in my name but also in the name of my colleagues from the Institute at the Institute, and of course at the Leibniz University of Hanover. It's my job to introduce you a little bit to what our institute does, what we are doing in research, but also teaching, of course. And yeah, let's get started. So maybe let's start with the terminology coming from our institute's name, photogrammetry and geoinformation. I'm not sure, maybe you've heard the term photogrammetry before, depending on what you studied before. If not, that's not a problem. I will give you an introduction, and probably in the lecture you will hear a lot about it. So even if you maybe didn't hear about photogrammetry as this term before, I'm quite sure that you have been confronted in everyday life in one or the other way. And I just want to give you a couple of examples where this might have happened. So the first point to see here is, for example, Google Earth. So you're wondering, okay, what's the connection between photogrammetry and Google Earth? Well, as you probably know, Google Earth uses satellite images as basis to do all their world views and so on, what we see when we open Google Earth, basically. And they also have a lot of 3D reconstruction nowadays and so on, so you can actually see the world not only from top, but also in 3D. And all of this requires a lot of pre-processing of the data. So it's not just drag and drop the satellite images to their viewer, but it requires some processing. And this is basically done by a lot of photogrammetry as well. In a similar way, we can use satellite images to visualize weather forecasts and so on. Roadmaps would be another example. Here, one application where photogrammetry is important is in the actual creation of the road network behind all your navigation, which would be the next point. So, maybe there are new roads built, or maybe some roads are not captured in the system. So this is where we, using photogrammetric methods, use, for example, aerial images or satellite images and automatically detect roads in them. So this can be used to then automatically or semi-automatically, if a human will check it afterwards, is used to update road maps. And this is what we use when we navigate with our cars and so on. There are a lot of more applications in architecture. Maybe you have seen visualizations of buildings, digital versions, not only of buildings, basically of any 3D object, which can be created using images of the object. And this process is also part of photogrammetry. So the definition, maybe a bit theoretically, let's still have a look at it. So it's defined as the acquisition and processing of information about objects and their evolution over time. So it's not only a stationary measurement, but we can also take a time series and analyze that one as well. Usually we want to get some sort of 3D information. Here it says shape, size, position of objects in space. So position, this would again relate to this example I just gave, where we want to automatically detect road networks. There we are interested in the position of road objects. So this is how this fits in there. But of course it's much more complex. So this actually includes object classification itself. So maybe we have an image of an object and we want to know what does it show. This would also be included here. Usually it's based on digital images. Of course, when you hear digital images, you probably first think about regular RGB images as you take them by most user cameras. But it's actually more than that. So we also work with height maps, for example, or distance maps in general. So where the value does not encode the color of a specific pixel, but rather the distance, for example. So it's not only RGB images. Remote sensing is defined as acquisition of information, blah, 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 without contact. based on radiation emitted or reflected from the object. So this can be active or passive. We have basically two variants. We can have passive sensors like RGB sensors, which use the radiation emitted from the sun, reflected by the object, then captured by the camera. But we can also have active sensors, like radar sensors, which emit a signal by themselves and then capture the reflectance. So this is why we have both in there. And we have actually a couple of colleagues with, who are working with radar data and not optical data, or not multispectral images. Yeah. So let's have a look at some practical applications which we address in our research, for example. And here in this slide we group them a little bit basically on the distance to the object. So we start very far away. The farthest images we can get is basically satellite images, which are captured from space. And nowadays we have a lot of basically freely accessible satellite images available. For example, the Sentinel images are making images of every or most of the area on the Earth 2 times a week, which is very useful to get time series and so on. And this is completely free. So we are working a lot with such data. Different applications like cartography, monitoring natural processes. For example, we are working on monitoring loss of forest areas in Germany, but also in Brazil currently. Catastrophe management, detecting floods and so on would be another possible application. So then we can get a little closer to the Earth and we end up with so-called aerial photogrammetry. We can use either planes, so this is probably the traditional way for surveying based on aerial images. Nowadays we also see a lot of UAVs, like drones, basically unmanned aerial vehicles, to obtain these images. And of course there we can do a lot more detailed mapping because we can actually identify individual buildings depending on the distance, maybe even cars, and much more. So we get a very detailed image from that height. And that is also used a lot, particularly for cadastral surveys, so to determine the outlines of buildings and such things. One specific case is photogrammetric image analysis. Here we are basically trying to convert the implicit information contained in an aerial images to explicit information like a vector map. So this includes several steps. We have to identify what objects are visible in the image, where are they, what is their shape, and so on. And in the end we end up with this explicit information, which can be, for example, used for navigation, because we actually have a good road map here. Then we can get even closer to our objects of interest, and we end up with so-called closed range photogrammetry. We have these subgroups like terrestrial photogrammetry, where we maybe take pictures outside but standing on the ground. Optical 3D measurement is another group where we are interested in the very detailed shape of objects. And you see in the applications we have, for example, industrial survey, which is very interesting. Like car manufacturers want to know, okay, if they build a specific part of a car, they want to know, okay, does it have the same shape as we planned it should have? Like, does it fit to the other parts and so on? So it's also for quality control very important. And they try to automate this process, because otherwise it would be very difficult if people would measure the distances by themselves and so on. And one way to do this is based on photogrammetry. You see that often those parts have rather a reflective surface where we don't have a lot of texture, which is usually bad for photogrammetry because we don't see the difference between this position and the position 2 centimeters to the right. So there are different ways to deal with this, and one would be this fringe projection, where we actually project a known pattern to the object, and then, for example, fringes like rings, and then measure how does these rings distort on the object. And this gives us information about the shape. And there are lots of other similar applications here. So we can also differentiate between the number of images that are used. So there are applications which are basically based on only single images, or maybe a single video, like a series of images taken with the same camera. Like we can do auto projection. You see one example to the right. We take this image from the side, and then measuring some specific points in the image, we can rectify it so that the rectified version to the right basically looks like we are observing it from above. We can do cartography, image classification, and semantic segmentation in single images, basically classifying objects in the image or pixel-wise classification as well. This is also interesting for applications like autonomous driving, where we have a monocular camera in the car and maybe want to detect if pedestrians walk in front of the car and things like that. Then we also deal with stereo photogrammetry, where we have a stereo camera, meaning basically 2 cameras, which enables us to do much more precise measurements of the depth. Basically, computationally, this is the only way to obtain depth. There are some learning ways to do this with monocular cameras as well, but that's a different topic. So this is usually having stereo cameras, we can obtain depth, like we do with our eyes. And this is very important also for quality control. We can get very detailed 3D reconstructions of objects, and then again check, does the shape fit to our expectations? We can use it for just modeling of 3D objects, and again for robotics, like again autonomous driving, but also robotics that try to grab things. They have to know, okay, how far is the object away, so they need depth information. In our institute, we have different research groups, basically dealing with the different aspects of photogrammetry and geoinformations I just showed. We have a small group also dealing with resolution and geometry, so with the sensor models basically. Then you have these 3 categories, more or less grouped by the distance again, and one group dealing with videos, so image sequence analysis. Okay. Lastly, I have 2 examples showing a bit of the versatility of the research we are doing. These are 2 projects IPI was dealing with in the past, but they are quite a nice example to show how many different topics we can actually address with photogrammetry. So the first one, we had a colleague who was working for surveying of the surface of the Mars. So there are satellites not only recording the surface of the Earth, but there are also satellites recording the surface of the Mars. And what he basically did, he was optimizing the procedure for the 3D reconstruction of the surface. And this is a very difficult topic because, as you can imagine, there's also not that much texture there, so they were trying to use the information from the craters and so on. This information was then used, for example, in the planning of landing of the robot Curiosity in 2012, but it was also used for reconstructing the surface in the film The Martian, which you may have seen. So different different use cases here for this product. And then a very different example of projects we have. This was a cooperation with a car manufacturer. And as you probably know, they have to provide these safety tests to show that in the case of an accident, the driver is actually safe. So yeah, they do this with these crash test dummies, having different sensors to measure the impact and so on. But usually they have to repeat the test several times in order to check for specific behavior of the person or the interior of the car and so on. So what we did in this project was actually use I think it was a stereo high-speed camera which recorded the scene during the crash, and then using this information we could get a 3D reconstruction, basically a slow-mo 3D reconstruction of the scene during the crash, and this helped the manufacturer a lot to basically make the cars safer, or to at least check if they are safe. This is a small selection of our partners in the past, but also in the present. So you see, there are a lot of car manufacturers, but also other research institutes like Fraunhofer, GLR, and so on. And this list is definitely not complete, so we have a lot more partners at the moment, but should just give you an impression. Okay, then. This is where you will have contact with respect to our teaching contents during your studies. So see, probably, one of the first courses you will hear is photogrammetric computer vision, given by Professor Heibke. Then we also have this acknowledgement course, 3D image processing and programming. I think it's mandatory for students that did not study geodesy here in the bachelor. So I was asked to remind you that this is a mandatory course, at least for most of the master students, for the international students, and it actually starts on Friday, so don't forget that. In the second semester, you will also see me again in the course Image Analysis 1. We have two parts, Image Analysis 1 and 2. First one dealing with rather the traditional ways of image processing. The second one is including also actually hot research topics, more or less, like deep learning and so on for image processing. And basically many basics of machine learning in general. Okay, so the main contact persons for you are the two professors of our institute, Christian Heibke and Franz Rottensteiner. You see it's not always the case, but at least formally, Professor Heibke is more dealing with all aspects of sensor geometry, 3D reconstructions, and so on. And Professor Rottensteiner is in the area of photogrammetric image analysis, more in the context of machine learning, deep learning, and so on. But this is not, as I said, always the case. And then we have Dr. Wegenhagen, who's also involved in a lot of lectures here, so you will probably get to know him as well. Okay, so that's it. Thanks for your attention, and good luck and a lot of fun during your studies here. It's very nice to have you back. Other questions?
Thank you. That was very helpful.
Good. Okay. This was number 3?
Yeah.
3 or 4?
Yeah.
Okay.
Yeah, okay, so hello, both of you. Welcome for the next or last presentation. So I'm here to present the IKG, which means Institute for Cartography and Geoinformatics. So this is the last of those 4 institutes. So you know the 3 others now, but yeah, just one is missing, I would say. By the way, of course, my name is Udo Feuerhake. I think we will meet again in maybe different lectures, for example, Internet GRS, so I will be responsible for Internet GRS. So at least we will meet again next Tuesday, same time. No, it's not same time, it's 2 o'clock, so 2 p.m. But I think it's the same room here. Okay, so those are the other phases of the institute, right? So on the top line, you see the different professors. On the very left is the head of the institute, it's Professor Seester. And then there's Professor Brenner and Professor Otto, and on the very right there's the secretary. And below there you can see the other different staff members which are also involved in different lectures and seminars and so on. So I think you will get in touch with some of them. Some will be more in the bachelor course, some are more involved in the master course. Okay. By the way, if you have some questions, just interrupt me, right? So this is, of course, not that problematic, but later, if there's something nice or if there's something you want to know in more detail, just interrupt me and I will try to answer your question. So what are we doing all the time? So the IKGs, what is the competences of the IKG? I would say it's written here, it's capturing, management, and analysis of geodata, and in the end, of course, you want to also present it, so visualize the geodata, right? So we just collect some data, some spatial relevant data, and the next question is, okay, how to store it, how to process it, and how to visualize the results, and in the end, right? It's always the same, more or less. And that's why there are those 3 main points here. So one point, of course, it's because it's also in the name, it's a cartography or the visualization. And the main question is how can we, as I said, present the data, and how can we produce nice looking maps, right? So it's not always that easy, so it gets very difficult if you have so many data. And there are some methods and some standard procedures you might get in touch later, which help us to provide reasonable maps which can be then used in other purposes, of course. And of course, the question is how can we visualize spatial data in general, right? So it's not always producing maps, but it's also some images or some nice insights into, for example, laser scanning data, 3D data. For example, also these head-mounted displays like the Oculus or Rift or whatever, right? So if you have VR applications, so this is also a field where we are working in, and it belongs also to this visualization aspect. Then there's, of course, a big field GRS, so geoinformation systems, sorry. And of course, there we are also dealing with spatial data, and we are looking for methods how to deal with and analyze and, in the end, again, present the data. And because also the name is geoinformatics, we have this geoinformatics part in our institute as well. And there we want to find methods which help us to automate processes. So for example, we can also do it manually, by deleting data, adding data, manipulating data. But the main question is always how can we do it automatically? So how can we write apps, tools, or whatever, which does the work for us? Now I want to just give you a small overview about the different lectures, which are mainly provided by the IKG. It's just, listen, maybe I can just go through it and say some words. I already mentioned Internet GRS, which is one of those starting lectures for you. I think it's a mandatory lecture as well. And it's dealing with how to present or how to create web maps, so maps in the internet on web pages. And so you'll have different kinds of maps, so you can zoom in, zoom out, and whatever. You may know this Google Maps stuff. So it's more or less creating your own Google Maps with all the stuff which belongs to it, right? So working on the client side, on the server side, working with databases, how to obtain objects or relevant information which should be displayed on this map, how to create this map by itself, how to style the map, and so on. So everything which is somehow related with producing maps and in the internet domain, of course. Then there's, of course, GRS Praxis 2, which is more or less the practical part of how to deal with spatial data in some sort of project. Laser scanning is another big field. I will come to this later again. So how to do the laser scanning and how to process the data which is provided by the laser scanners. GRS for Fahrzeugnavigation, so for navigation applications. It's just like it says, right? It's navigation purposes, so which algorithms could be used, Dijkstra, R-star, whatever, and what else is important for doing navigation for vehicles and so on. GRS application, the new research directions, a big module which consists of several lectures. So here is those three mentions: application, new research directions. So it's just a set of different fields which gives some insight into new branches like machine learning, artificial intelligence, how to analyze spatial temporal data, so the spatial data together with the time aspect, multiple representations, so have a look on data on multiple scales, and so on. So there are different fields, and you always get some insights into it. GRS practice and visualization aspects is more like, so there's a set of lectures given by different staff members, and they are presenting their work, their project they are currently working on. So we will also get some insights which are somehow related to the first part of this lecture. Geodata infrastructures is given by Mr. Vilgares, who is an external lecturer, and he's working in the, how is it called, LGLN. It's the surveying agency of Lower Saxony, right? And he will give you some overview about the infrastructures used for storing, handling, and analyzing geodata. So it's more or less some technical part, but also something with the rights, the laws, and so on. Monitoring the spatial temporal network data is given by Professor Otto. SLAM, path planning. I think this is an online lecture. This is quite interesting, and I think it's a very good lecture as well. Dealing with somehow localization and mapping together. Geosensor networks is given nowadays in the summer semester, so you can't do it in this semester. Hauptseminar and project seminar are two seminars, so which are where you are more or less doing something in a group, and I think this is a lecture or a seminar which is working all over the institutes. So you get different topics, then you will create a group of whatever, 3 to 5, 6 people, and then you get a special topic and you're working it for one semester, and afterwards there's some final presentation, and then you get the credits, of course. And I think there are mainly nice topics in those seminars. Okay, so this was a brief overview, and I think you will learn about this later, of course. Now I want to present you some selected topics, some research topics which are currently done or have been done in the Institute by other colleagues, and this is just an overview about the different fields, right? So we have different research fields in our Institute, starting with the big data machine learning part, and there's data integration, generalization, 3D visualization, laser scanning I already mentioned, mobility is a very big field, and of course the robotics. And I want to go into detail first with the laser scanning. And here what you can see here is our mobile mapping van. So it's just an ordinary van, but it's equipped with a mobile mapping system. You can see it in the top left, so on the roof. It's a system which consists of 2 laser scanners, 4 cameras, a GPS antenna, an IMU, several PCs, and it just records, or it just does the laser scanning and records points, 3D points of the environment. So you can just drive through a street and just records all the 3D points. So and on this slide, you can see one sample, which results from the system. You can see all those tiny points are just single points and colored by the height. So the more red, the higher it is. That's why there's this rainbow color here. But you also can see those little details, right? So it's very dense and so on. So you can see those single stones on the pedestrian walk, for example, here on the bottom left. You can see those people sitting in the chair in front of the restaurant. You can see the details of the facades of the buildings. So it's very dense, right? So you can see more or less every detail. And that's why, so on this slide is given, there's 600,000 points per second. Yeah, so and if you have one project where you just drive 1 hour, so there's an insane number of points in the end. And you, of course, cannot do it for just a small sample, but you can also do it for one complete. Also, at least our goal is to do it for complete Hanover, right? So, of course, it takes a lot of time to measure it and to store it and to process it afterwards. Yeah. However, we also have the problem that if you just drive through a street twice, for example, like given here, and because there might be some noise in the positioning of the car, maybe the GPS is somewhat inaccurate, or you do not get the very same position as before. So you will get 2 point clouds. Here, one is colored in green and one is colored in blue. And you see there's a slight shift, right? So for example, the sign next to this car here, for example, you can't see my mouse, so here it is. Here's a street sign, yeah, just looking from top. And you see there's a small shift because the position of the van is not the same anymore. Yeah, and so one task is to make it one. So, which means you have to remove these displacements, yeah, and you use some algorithm which pulls the point clouds onto each other. Yeah. And then you might have something like this. So this is one point cloud, right? So you can see this facade with the entrance of the building, this small wall in the top end of the street. Maybe we go there several times. Yeah, you see the different point clouds, different colors here. And afterwards, after this alignment of these point clouds, so we move everything onto each other, then you can have a very, very, very detailed point cloud. So this is still points, yeah, but there are so many points that you just see those surfaces here. Yeah, and you can nicely see those those plates on the pedestrian walks and the different heights. Yeah? So this is just millimeters, but you can directly see it in these point clouds. So it's very detailed here. What else can we do with those point clouds? Of course, we can also measure the city or the streets, or the room of the streets, and then we can try to identify or distinguish stationary and dynamic objects. Yeah? Stationary is the infrastructure, the houses, the streets, and so on. And then we have something like cars, which move around all the time, or this vegetation, which loses leaves in the winters, and so on. And if we can detect those cars and moving objects, so we can easily remove them. Yeah? And so we can get a plain city or plain street or whatever. And this kind of data is, of course, more useful as such with those disturbing moving objects, right? For example, if you want to do the positioning, and you're looking for landmarks, maybe those landmarks are somehow hidden behind those cars. And if we can remove it, then it's much easier to process it afterwards, right? This is a nice picture. That's why it's in the slides here. It's just, the idea was to find regions in those point clouds. So, for example, we want to detect planes, right? All the points are connected, which are somehow on one plane. So you see all the different colors which are representing different planes. You see those big facades, but you can also see on these cars here, for example, on the bottom. This one here, for example, you see one plane for the side of the car, one for the roof, one for each of those tires or wheels, and of course one big for the street. And afterwards, you can also use these planes for further processing. But the main point is it looks nicely, and that's why it's in the slides. Okay, so this was the laser scanning, which is, as you may see, it's a very big field at our institute, right? And another big field is, of course, the processing of those point clouds, of these results. And this is mainly done by methods of machine learning or big data analysis methods or whatever. One colleague or one former colleague processed the point cloud in that way that he wants to give a meaning to those objects or to those points you saw in the previous slides. Yeah. So those points were just single points without any meaning. Just say, okay, the distance to the car was something. So you get just an environment here, but you don't know what it is. Actually, you can maybe, you as a human being, you can directly see those red stuff is cars, for example, because you know the shape of the cars, but the computer doesn't know. Yeah. And the idea was now how to make the computer know that this one is a car, for example. Right? And that's why my colleague used some machine learning, or in this case also some deep learning methods. He used the convolutional neural network in order to train it and to learn which kind of object it is. Yeah. So in this case, he tried to identify the street, the cars, the houses, the sky. Now sky is not relevant. All kinds of objects, right? And so he trained it a lot with our data we collected. Then he did some manual assignments, manual labeling, and so on. And afterwards, after he trained this network, he just applied it to the data. And what you can see here is the result, where the colors show the different kind of objects. So this purple, for example, is the ground plane with a street, for example. Then you see all those green vegetation, like trees and so on. In gray in the back, I hope you can see it, there's the facades of the buildings, right? And in blue, you see the different cars. I think in yellow, you can also see the street signs here, somewhere in the back. That's street signs, street lights, and whatever. So you have a meaning. I think in red here, this one is the pedestrian. Yeah. So you have not only the points but also a meaning to the points. Yeah. And then you can process it and use it for other purposes. Other purposes is, for example, later I will come back to this in one of the next slides. If we want to detect some parking lots where you can put where you can bring your car somewhere, right? And this is not given in any OpenStreetMap data or Google Maps or whatever, so we had to detect it by ourselves. We can use this kind of data or this kind of results here, and we can first detect the cars and then check whether there's a parking place. Yeah? Okay, but however, for another machine learning, another colleague, which is still at the Institute, uses also some machine learning tools, deep learning again, in order to find a method in order to predict street heavy rainfall or pure floods events, and he used simply social media data, so mainly Twitter. So he passed all the Twitter posts for a certain time period. Then he checked images or posts with water, rainfall, all those different keywords, right? And then he tried to analyze those images, like given on the top right here, right? He just checked what is the water height, how much rain it was, and so on. And then he used this kind of information and tried to georeference it. For example, this photo here, maybe there was a georeferencing by the uploader of this photo, so he knows the place, and maybe he also knows the water height, so he can just put it to a map in the end, right? So he did it. He did it for many of those photos, of course. Then he can produce something like this, shown on the bottom right, where you can show some heat maps, with the amount of rainfall for certain locations. And in the end, of course, he used for this analysis of the pictures and the text, he used some neural networks again. But at the end, he produced some kind of map where he can say, okay, there was some flood events in this part of the city or in this region of the country, and so on, at a certain time, for example. And then you gets further information for it. This could be, of course, quite useful for some use cases. One of the last big fields is the mobility field, and there's a lot of stuff in it. I already mentioned this dynamic parking. Yeah. So the question is, if you want to leave your car somewhere in Hanover here, in some places it's not easy. Here it's quite easy because there's so much space, but if you go to another region in Hanover, there's just few parking places, and all of them are occupied all the time. So the question is, if you want to go there, it would be nice to have a navigation system which also recommends you a parking place. But unfortunately, in OpenStreetMap and Google Maps, this feature is not available. Yeah, of course, there's these big parking places, but if you want to put it next to the street, so on-street parking, there is no information about this. right? And so the idea was that we can generate this kind of information by ourselves. And of course, we also used our mobile mapping van, drove through the city, drove through certain streets several times a day. And then we collected those point clouds, analyzed those point clouds, detect the cars. So we got this kind of, these lanes of cars here, for example, right, next to the street. So we might get a hint that there might be a parking place. So if we do it more often, then we are at the end very sure that there's a parking place because there's always a new car and so on, right? And we also get some information about how often it is occupied and not occupied, right? So and then we can use this information, put it to a map again, like shown here in the middle on the right. So this is a parking places in blue next to the street or on the street. And then we can, since we drove there several times, we can also estimate the free times and occupied times. And we can give an estimation when it's free and not. And of course, this kind of information you can just directly feed into a navigation system and say, okay, now I want to go to the university. Yeah, please guide me to one free parking place. And then it says, okay, go there or go there. This is the idea of this little project. Another big topic in this field mobility is the analysis of spatial, or not spatial, it's spatial temporal data, so it's an analysis of moving objects. And moving objects can be anything. It can be vehicles again, yeah, so what you can see on the left is the trajectories of cars. Yeah, so there are a lot of cars, there are millions of trajectories in this data set, so you can have a very close look into the behavior of the cars and so on. On the right-hand side, you can also see it's also working for animal data, right? So you can just use the traces of the animals in order to analyze their behavior in the end. Yeah, where do they go, where do they eat, and so on. Are there group movements, group movement patterns, and so on. On the bottom right, there's also the possibility to do the same for the football players. Yeah, you can also collect the trajectories of the football players and analyze their performance afterwards. Yeah, so you can check their covered distance, the plate passes, the whatever. Maybe you have seen it in the television, when you saw a football match, there's always some direct analysis showing some heat maps and some whatever, right? Some statistics about the distance of the player, the number of fouls, and so on. Right? And you can. Our idea was, in this case, it was my idea because it was my project. For the professional clubs, it's easy because they have a lot of money and these services are quite expensive. So it's easy for them, but if you do it for non-professional soccer players, of course it's not possible because it's too expensive. So the idea was, is it also possible with cheap equipment? Yeah, so not with those with these arrays of cameras in the stadium, but is it also possible with those tiny GPS loggers plus one action camera or whatever? So very cheap setting. And our idea was to use a new tracking method which uses both kinds of data in order to make it better, to improve it. And it nearly provides comparable results. Yeah, of course the professional stuff is better, but it's usable. And afterwards, of course, we need some software to analyze those the trajectories of the players. And this software was able to do this statistics stuff again, distance and so on, but also to detect some patterns in the movement. And this is important because it's nice to know the distance of the player, but it's more like, it's better to know where he wants to go next, right? So to predict movements, for example. And if you know the patterns, so you know the typical behavior of a player in a certain situation, so then you can predict it, right? And the question was how can we recognize those patterns in those kind of data? And the data, if it comes from those tracking solutions, looks like this here. It's just a set of samples where you have location, X, Y, Z, and the time, for example. Maybe the player ID and whatever, but this is how it looks like. And then you can visualize it, of course, and then you can have to create some algorithms which are able to analyze such kind of data, and of course to find those patterns like shown on the bottom right here. Okay, one of the last slides is, in one of the last slides I just want to show you these quite new project, I would say. It's a Right Vibrations project. It started with a student project in one of those project seminars I mentioned in the beginning, right? So this was a group of students which started to create an app for a smartphone app, and this app is able to measure some values, some values. The idea of this project was if you want to go by bike from A to B and you don't want to use the fastest or the shortest route, yeah. If you want to use the fastest and shortest, you can use Google Maps and then you get some route. But if you want to use the most comfortable route, for example, or the safest, right? Those features which are required, like the surface quality or the illumination or how many streets are close by, or not streets, how many cars are close by, or all the stuff is not given in Google Street Map. Sorry, OpenStreetMap or Google Maps. So I want to say both. So I mixed it up, but it doesn't matter. So the idea was that we also can provide the safest or the most comfortable route to the bikers, right? And so we have to collect the data by ourselves again. So that's why there's this app called RightVibes, and this app is able to measure the vibrations of the ground. So it was adjusted to these handlebars of the bike. And as soon as you ride through cobblestone or whatever, which shakes a lot, of course you get a very shaky road, right? And you can see it partially here in this map. So everything which is quite wet, there's a strong vibration, and of course it doesn't feel comfortable for the rider, right? So this street here in the top is, for example, is cobblestone. That's why it's dark red. And normally you wouldn't go there by bike. Yeah? So the question is now, how can we do it automatically? That's why we have an app. And we have also some backend where we analyze all the data which is incoming. The data looks like this, for example, but we want to produce some kind of map. So there's a lot to do in between. And in the end, as I said, we want to have some navigation which guides you through the most comfortable or safest routes. Okay, so this is a pre-last slide, and I just want to present our web page. So if you will find additional information to all of what I said here before. You can have also information about the different lectures again, some nice descriptions. You will also find open topics for master and bachelor thesis, which is important in some years, 2 years maybe. 1.5, I don't know. And maybe also some open HEVI and PhD positions. It a little bit depends on the projects which are currently running and so on, but you can have a look at it. Yeah. And next slide. Yeah. And so to sum up, I just presented you what the IKG does. So it's more or less, we have a wide range of application areas. And one focus is still the automation of processes, yeah? So that's geoinformatics still, right? And of course we're dealing with spatial data, but the idea is always to do it not manually, but to do it automatically somehow, right? There's a little bit of programming all the time, but this is our main focus. And last but not least, I want to wish you, and also the IKG wishes you the best for your studies, and have a nice time here in Hanover. Thanks. Okay. Other questions? Okay. No problem. No problem. Thanks. Danke.